There's a classification of molecules which have the capability of behaving like an acid or a base depending upon the chemical environment. These molecules and ions are said to be amphiprotic, meaning they can donate an H ion or they can accept an H ion. So I've got 3 examples here. We'll talk about carbonate, but you can see there that water is also a neutral molecule, which is amphiprotic and turns out to be quite important, as we'll see in a little bit. So amphiprotic reactions take their molecule, and when they are dissolved in water, they can produce either a hydroxide or a hydronium ion. So in that first reaction there involving bicarbonate being in the presence of water, it creates the carbonate ion and also creates the hydronium ion, or it is the same as an H plus ion. Those 2 ions are essentially the same. On the other hand, bicarbonate can also react with water to extract a hydrogen ion from water to create carbonic acid and hydroxide, and that's the second reaction there. Now, when we talk about writing dissociation reactions involving acids and bases, we often use the term conjugate to indicate where the ion that results as a product came from. So here we've got nitrous acid, which is an acid, reacting with water, which is, in this case, behaving like a base. So the first thing you have to do in identifying conjugate acids and bases is identify one of the 2 reactants as either being an acid or a base, which would make the other molecule whatever you defined as being the opposite. So water is a base in this case because it's reacting with an acid. So once you've identified your reactants, what you do is then move over to the product side and find the ion that corresponds to it, in this case the nitride ion, and we say that the conjugate is the opposite, so nitrite is the conjugate base of nitric acid, and hydronium ion is the conjugate acid of water, which in this case is a base. So you'll notice the conjugates are always products and opposite of the molecule they started with. So let's take a look at hydrochloric acid dissociating into water. HCl is the acid, which means water must be the base. Does that mean water is always a base? No, just in this particular reaction. So we've got hydrochloric acid, which is an acid, and when we go to the product side, we see that the chloride is the molecule that comes from HCl, so that would make it the conjugate base. The water, which is a base, becomes the hydronium ion, which makes it the conjugate acid. Let's try another example. H2SO3 plus H2O. Again, H2SO3 is an acid, making water a base. And when we look at the conjugates, again, we see H3O plus is an acid. It's the conjugate acid. H3O plus will always be a conjugate acid whenever you see it. And HSO3 minus is the conjugate base. So Bronsted-Lowry explains acid-base properties. Acid strength is measured using what's known as a p-scale. So we talk about the acidity level or the concentration of H plus in terms of pH. pH is simply the negative log of the hydronium molarity, or H3O plus molarity. The pH scale typically seen goes from 0 to 14, but in reality goes from -1 to 15. And anything from -1 to 1 is considered incredibly acidic in terms of concentration. Doesn't necessarily mean it's a strong acid, but it means it's highly concentrated. On the other hand, pH 14 to 15 means it's incredibly dilute with hydronium or acid content, and in fact we actually say the opposite. We say it's incredibly basic. The pH scale is based off of the reaction involving water undergoing autoionization, that is, two water molecules react to create a hydroxide and hydronium ion. And when these two ions are at equal concentrations, we're said to be neutral. Well, on the pH scale, neutrality occurs at pH 7. So pure water has a pH of 7. Things that are incredibly acidic, like hydrochloric acid or lemon juice, which has a pH of 2, fall more on the acidic side of the pH scale. However, Windex or ammonia, drain cleaner, those fall on the basic side or the alkaline side of the pH scale. So we have varying degrees of acidity or alkalinity as we describe basic side. So we've got this relationship of water to hydronium and hydroxide ions. And as we said before, water is amphiprotic. It can behave like an acid or a base, and in this case it's behaving like both. In pure water, there's only a few hydronium and hydroxide ions, and when water undergoes this reaction to create hydronium and hydroxide ions, we describe the process as being autoionization. That is, these two molecules are capable of ionizing themselves without outside assistance. So when we talk about equilibrium as it pertains to water and our pH scale here, we write an equilibrium expression where we say two water molecules, which are reactants, produce hydronium and hydroxide. And when we write our equilibrium expression, we say the equilibrium constant, or Kw in this case, referring to the water autoionization reaction, is equal to hydronium times hydroxide. And so at 25 degrees Celsius, this Kw, or ion product constant for water, is 1 times 10 to the minus 14th. That's a number you're going to have to remember yourself. Any other temperature, I'll give you Kw. If I don't give you Kw, just go ahead and assume it's 1 times 10 to the minus 14th. As we know, temperature causes equilibrium constants to change, which means that pH changes with temperature. So the neutral point of water is pH 7 only at 25 degrees Celsius. So how do we relate pH? Well, pH is great for an acidic scale, but sometimes we're dealing with bases and it's easier to talk about hydroxide concentrations. Well, we can relate hydroxide to hydronium ion concentrations through this Kw expression. So we can relate Kw through our expression here and talk about finding pH and pOH. So pH is just the negative log of the H plus molarity. pOH is the negative log of the hydroxide concentration. Any solution that has a pH of 7 is defined as being neutral. Any pH below 7 at 25 degrees Celsius is defined as being acidic. And any solution above pH 7 is considered basic or alkaline. So we have this relationship here, pH plus pOH equals 14. And this is true at, again, 25 degrees Celsius. But if you know the pH, you can find the pOH. If you know the pOH, you can find the pH. And if you know the pH, you can find the H plus concentration. And if you know the pOH, you can find the OH minus concentration. So pH and acidity and alkalinity are all related through this expression.